everybody, I thought it was finally time to take the Graff Generator out. Now this is something you've seen since grade school. Almost everybody that's in this class, it's at one point or another, went to the Boston Museum of Science and saw the world's largest Graff generator, which is awesome. It's pretty cool. What I'm going to be able to do here is to be able to store a large amount of electric charge using something called a Leyden jar. And really the Leyden jar was the first capacitor. So before we get to that, I at least wanted to show you a little bit of how a Graff generator works. Hopefully you can see this diagram okay. So what's happening in a Graff generator is that there is a rubber belt that runs up the middle of the Graff. Down at the bottom, it's actually connected. There's a small bit of charge that's established on a screen. That screen rubs the excess charges onto the rubber belt. Now, because the belt is such a good insulator, it's going to carry those charges up to the top. Now, up at the top, there's another screen where those electrons, as they apply a force to each other, are going to jump off onto the screen and then spread out on the sphere. If we actually take a look at a Graff up close, you can see, hopefully, right in there, you can see the screen and the rubber band that carries the charge. And because the sphere here is fairly large, we're able to collect quite a bit of charge on that sphere, which creates a very large electric potential, a high voltage. Now, the thing is that this Graff generator is surrounded by a really good insulator. Do you see it? Oh yeah, it's right there. I can feel it. It's surrounded by air, and because of that, all of that charge gets stuck right on the sphere. So when that charge gets stuck on the sphere and it's surrounded by this insulating layer of air, it has nowhere to go. And it'll build and build and build until it really can't hold any more charge. And then what happens? Hopefully it discharges, but not onto me. Here, I have a little copper ball. It's connected to a wire here that is connected to the actual device. Now, this wire connects to the ground. Now, that is literally connected to this end of the plug that we call the ground plug, and that is connected to the wall, which is in your electrical system connected to a copper rod out in the, yeah, that's right, it's out in the ground. That's why we call it that. So, what I'm going to do is as all of that charge collects on this beautiful sphere here, I'm going to allow it a path down to ground. That's where we see the discharge. So, now, I must admit that every time I start this demo, my elbow starts to hurt. And basically, I've shocked myself so many times that, like Pavlov's dog, I've developed a little bit of a fear of this, a physical reaction, I guess, in anticipation of a stimuli. So, hopefully, this goes off without a hitch. If not, it'll make a good YouTube video. So, I'm going to turn this on. Increase the speed of that belt as it moves. And what's happening is that there's a pretty large potential established on that sphere. And if I put this ball close enough, we can see it start to discharge. Now I'm going to hit the lights. Hopefully, you can see that discharge. Now, the obvious problem of doing this in the dark is that I don't know if the video is going to work. And second, I'm always afraid of shocking the heck out of myself because I don't know what to touch. Cut! Do you guys realize I'm a one-man production crew? I have to shut off my own lights, probably get the defibrillator out for myself when I shock myself and end up on the floor. I gotta edit the whole video. This is nuts! So, discharge check. Now, how do we know that there is a field out there? Well, the classic demonstration would be to have somebody put their hands on top and show the charges applying a force and causing somebody's hair to stand up. I tried that earlier, and there wasn't a lot to see. I tried it with a wig. Again, didn't work. But what I do have is a video of Mr. Keene earlier today. Now, Mr. Keene has beautiful hair. I don't know if you guys know this, but Mr. Keene is actually older than I am. God, he's so healthy. He's so healthy. Let's go to the tape. I'll have to put in some audio later. And cut. Oh, look at that. Look at that. Wow. What beautiful hair. Thank you. All right. Hold on. I don't want it to discharge onto my computer. All right, go ahead and step down. Excellent. Good. Now, here, I've actually given it a bit of its own hair. This is foil that you might use, say, around Christmas time to decorate a tree. Let's see what happens if I connect that foil to the sphere. What do you think is going to happen? Yeah, I know you know. I just think it looks cool. Let's give it a shot. You can see that almost instantly, the electrons try to get as far away from each other as possible. And you can see that as I bring this closer, they'll discharge back to the ground. But what you'll also notice is that as I bring it closer, I'm no longer able to get a spark. Or when I do get a spark, watch what happens to the hair. It jumps down because there's a discharge at that moment. I hope that shows up. Now, I'm going to turn this off. Make sure I touch that. Another quick demonstration I have is what's going to happen to bubbles. Now, bubbles are neutral because they have the same amount of electrons and protons. But as they enter the large electric field that surrounds this sphere, they get a charge separation in the actual bubble. Now, the bubble remains neutral overall, but since one side is more positive and the other side is more negative, it ends up being attracted. Now, every once in a while, you'll get one of those bubbles that actually picks up a little bit of charge. Do you see it? Right there. When that happens, it's picking up a little bit of charge from the atmosphere, from the charge from the air around. Oh, there's a good one. When that happens, it repels because it's gained excess negative charge. All right, so when it comes to the flow of electricity, we've been saying it's the flow of positive charge. And everybody gets upset because we all know it's actually electrons. And who was it that made that mistake? Yeah, it was Ben Franklin. He thought electricity was the flow of a positive fluid. Not that far off, but the nomenclature is different, and because of that, well, we're stuck talking about the flow of positive charge. So while we make fun of Ben Franklin for that, we really should acknowledge the work he did with lightning rods. Now, my guess is that you, much like everybody else in society, doesn't really understand the purpose of those lightning rods that you see on the corner of buildings, maybe on the top of a barn, somewhere close on a hill. if you have a building on a hill, it often has lightning rods on the top. Most people think it's so that the electricity will actually flow and hit that, flow through the wire down to the ground. And while that can happen, that's actually not its primary purpose. Its primary purpose is to actually allow for a discharge off of those corners, creating less of a potential difference. Now those are just words. Why don't we see what happens? I'm going to carefully turn this on, not shock myself, hopefully. And I think you can see, if you can't see, you can at least hear that it's discharging anytime I get that closer than a centimeter or two. I get a really nice discharge. All right? But what happens if I take something with a sharp point on it? Say, like an old school metal tack. And it, oh, damn it! Darn it! And I take it and I put it right there. Now, can you see that sharp point? That sharp point is going to allow for the electrons to jump off into the air. Let's see if I can film that. Stupid. Here we go. I do try to keep this thing between me and the Van de Graaff, allowing it to discharge. All right. I'm not going to show that part. All right, let's try that again. Ready? I try to keep this in between me and the Van de Graaff. So you can see it discharging again, but watch what happens as I bring it near the top. It no longer discharges, because what's happening is that electrons are actually bleeding off into the air at that point, decreasing the difference in potential. I'm going to shut the lights off, and maybe we'll get to see a better view of that. Whew! It's pretty dark in here. Let me try that again. Ready? Here we go. So I'm hoping, oh, yeah, there we go. You can see that discharge. But as I bring it closer to the top, now it's down low. As I bring it closer to the top, it's gone, it stops. It doesn't allow it to discharge. So what it's doing is it's bleeding off that excess charge. Now, I'm going to try to see if we can see something called St. Elmo's fire. Hang out there for a second. Whoo, it's dark. Ah. All right. Now, St. Elmo's fire is what happens at the top of a sailing ship when charge actually bleeds off of the mast. And you can actually see it glowing. So I'm wondering if you guys, if we are able to see the tip of that glowing purple. I guess we'll have to check that out in post-production. But for now, let me see if I can turn this off without killing myself. So this is one long, crazy take. I have no idea if this thing's going to work. If it doesn't, I'm going to be really disappointed. In fact, you know what? I think I'm going to stop it right here. The part I really wanted to get to today was a Leyden jar. Now you saw the charge that was discharged by the Van de Graaff through the air. And while it did hurt, it wasn't that dangerous and it wasn't a lot of energy. In fact, it wasn't enough to cause a burn or stop my heart, fortunately. The Leyden jar, on the other hand, well, that's a different story. Because what we are able to do with a Leyden jar is to actually store electrical charge. This was the world's first capacitor. Let me explain how it works. What it is a glass jar. Now this glass jar, okay, right here, has a wooden top and a metal brass piece that comes out with a ball on the top. That piece is connected to a chain that sits inside here. Now glass is a good insulator, so the charge can't go through the glass. But what it can do is collect on the metal foil that's on the inside of that jar. So I can force electrical charges, maybe by putting it up against a Van de Graaff generator, to travel down and collect on the inside of the Leyden jar. Now when they do that, they create an electric field. That electric field is going to force the electrons off of the outer surface. If I take the outer surface and connect it to ground, that can cause the electrons on the outer surface to run out to ground, leaving behind a positive charge. And then we end up with a large potential difference between the inside of the jar and the outside of a jar. If we connect a conductor in between, what will happen is the electrons will move. What are moving electrons called? That's right, electricity. So what I'd like to try to do is to demonstrate how much charge I can store on that Leyden jar and not electrocute myself in the process. If somebody were to find this video later, you should know, well, and I'm on the floor dead. I knew the risks. I knew the risks. All right, so with that, let me get things set up. Here we go. So I've got my Leyden jar sitting in a foam cup. Great insulator. Charge is not going to be able to go from the outside of the jar down to the ground. But what I am going to do is I'm actually going to connect a wire to the outside edge of the foil. That wire, I'm going to connect it straight down to ground. Okay? Next, what I'm going to do is I'm going to turn the Van de Graaff generator on. It's going to discharge over and over and over again into our Leyden jar, and it's going to store up that charge. Once it starts to slow down, the capacitor is full. It has stored as much electrical charge and energy as it can at a given voltage based on its capacitance. Oh yeah, it sounds like capacity, doesn't it? How much we can fill it up. So once it stops charging, I am going to pull this away and disconnect the ground. And then I'm going to use this device here in order to touch the inside of the jar, which would be that point right there, and the outside of the jar. And we should see a pretty big discharge. Now, because this scares the heck out of me, I'm going to use my linesman's glove. It has a high voltage. And since there's nobody else in the building, since it's Friday afternoon, yeah, they might not find this till the morning. Sorry, honey. All right, so I'm going to plug this bad boy in. I'm going to stand on a piece of wood so that I am not an attractive path for electricity to go down. Turn it on. And I can already hear it discharging. I'm going to move that a little closer. And we can start to see it charging. Can you hear it? Yeah, that's good. That's good. Geez, that's charging a lot. I can hear it starting to slow down a little bit. Huh? Well, it's pretty charged. Let's see what happens. I'm going to go ahead and turn this off. Ooh, I can hear it discharging out into the air a little bit. I'm going to unplug it from ground. Not bad. Should we try with the lights off? So, to up the degree of difficulty, it's more fun to try to do this in absolute darkness. I'm good, I think. All right, here we go. Ooh, you can see it discharging into our Leyden jar, collecting more and more charge. Storing more and more electrical energy. Oh, I see a little bit of discharge on the inside of the jar. Neat. I'm going to turn this off. Oh, I can hear it bleeding off. Shh. Got a lot of tension. Ho! That wasn't what you were looking for, is it? Take two. Storing more and more charge in that Leyden jar. All right, let's see what happens. Damn. And that's a wrap. There you have it. Leyden jars. The world's first capacitors. They store electrical charge and energy, just like a modern day capacitor. Was that spark as dramatic as you hoped? No. Am I still alive? Yes. I'm going to call that a win. All right, let's get working on capacitors. Thanks.